Today, we want to continue talking about our fundamental theorems of calculus and think about our two new ones that showed up, despite the fact that I have not talked about curl or divergence or what S, W, and C and what all this stuff is. So we see that the fundamental theorem of calculus for line integrals fits with our original fundamental theorem of calculus, where the gradient is acting as the derivative. The set over which we are integrating is some one-dimensional path from point P to point Q. The function that over which we're going to evaluate the boundary, the function that we're going to evaluate at the boundary is our potential function f, and our boundary is just the endpoints of our path, starting at P, ending at Q. So the fundamental theorem of calculus for line integrals really fits with our OG fundamental theorem of calculus, if we soften our focus and think of the gradient as being the derivative of this potential function, this weird vector derivative, but it's made up of first partial derivatives, so it makes sense. In Stokes' theorem, things have changed. We're integrating the curl of this vector field f dot dA over some surface S. So yesterday I did mention that S is a surface. That is the set over which we are integrating. The curl of f, the curl of the vector field f, looks to be standing in as the derivative of our vector field, which is standing in as the function. And so C is the boundary of the surface S. So here we are evaluating the function, in this case of the vector field, at the boundary of the surface S, which is some curve C. So our surface integral of the curl of this vector field is a line integral of the vector field itself. So when pairing up Stokes' theorem to the fundamental theorem of calculus, it looks like the curl of f is acting as some kind of derivative of this vector field. Some kind of, specifically some kind of vector derivative of a vector field. Different from the gradient, because the gradient is something that we apply to a scalar function. Gradient is some kind of vector derivative of a scalar function. The curl is some kind of vector derivative of a vector field. In the divergence theorem, I guess whoever came up with divergence theorem didn't get to put their name on it. Well, what if their name was divergence? And that's why he called this divergence. That would be weird. Excuse me, Dr. Divergence, I have a question. That would actually be an awesome name. Just be Dr. Divergence. In the 21st century, that's your social media presence. Hi, welcome to Dr. Divergence. Starts a whole math TikTok. Only goes viral because he starts doing like a TikTok dance. Anyway, so in this case, W is a solid. So we're integrating the, the divergence of this vector field over some solid, but not dot dv. dv is just some chunk of the solid. dA was a vector. In Stokes' theorem, this dA is a vector. But in the divergence theorem, dv is just some chunk of the solid, no vector attached to it. If we think about the boundary of a solid, the boundary of a solid is going to be a surface, and that's what we have on the other side. S is the boundary of the solid W. So here we're integrating the divergence of F, the divergence of the vector field F dV, by evaluating the vector field at the surface of the solid. Just like in Stokes' theorem, where we're integrating the curl of the vector field F dot dA over the surface S by evaluating the vector field at the boundary of the surface. Just like we integrate the gradients of a scalar function F along a path C from point P to point Q by evaluating the potential function at the endpoints of our curve. So from a certain point of view, the gradient of F, the curl of the vector field F, and the divergence of the vector field F, those are the things that are standing in as the derivative. This is all in terms of our structure. The integral of a derivative over a set by evaluating the function at the boundary of the set. So these are all acting like derivatives from a structure of the fundamental theorem of calculus standpoint. So we need more stuff to pull this together. We need more stuff to pull this together. And that's going to be the operation that we have that connects gradient, curl, and divergence. So use this upside down triangle. I think the intention is to be an upside down delta. The del operator is a vector. Specifically this vector. The I component is the partial derivative with respect to x. The j component is the partial derivative with respect to y. And the k component is the partial derivative with respect to z. So it's an operation that we can apply. It's this weird vector operation. We can apply the del operator to a scalar function and also to a vector field. So del operator can be applied the del operator can be applied to a scalar function f or a vector field f. Sometimes I wonder if capital letters were a good idea, but I mean, we're stuck with them now. We look at the del operator, it's a vector. We can apply it to a scalar function, or we can apply it to a vector field. Remember, a vector field is going to be a vector. So we have one instance of a scalar function and two different instances apply when we have a derivative thing applied to a vector field. One is a vector and one is a scalar. The curl of f is apparently some kind of vector, and the divergence of f is some kind of scalar. So if you start thinking, if you're thinking, are we going to be multiplying this del operator by our vector field in the two different ways that we have to multiply vectors, then you are correct. One is going to be a cross product and one is going to be a dot product. This math stuff is so predictable sometimes. It could be a movie. And sometimes I wonder if it should be a movie. Because not many people are going to show up to see Calculus 3 with Professor Leach. But think about the box office smash, Calculus 3 with Dwayne "The Rock" Johnson. That would be awesome. I would go see that. Now, he wouldn't be able to work with a like a pad of paper like this. You'd have to stand at the board so that when students ask a question, he could turn to the students and do the eyebrow thing. But I think I would definitely go see that. I want to get Dwayne "The Rock" Johnson to come do a guest lecture in my class. I'll tell him what to say. I'll give him a script. I mean, he's an actor. He could do that. I think that would be awesome. People would show up for that class. Anyway, what are we talking about? So we're going to apply this del operator to a scalar function. And then we're going to apply the del operator to a vector field in two different ways. Now, none of this, all of this is going to be mechanics. None of this is going to give us an idea about what's going on. Our intuitive idea about what's going on beyond just mechanics of shit, that we have to think about. But let's get our mechanics first. It's like back when you learned how to multiply. You learned how to multiply. You learned your times tables out to 12. You learn that before you learn what multiplication is for. Because, I mean, some of you are taking physics classes. You're still learning what multiplication is for. So you learn the mechanics of multiplication. How does multiplication work? You do that when you're children, because children don't ask, why do we have to do this? And I go, okay, this is the thing that we have to do. Adults that we trust said we should do this thing, so let's do this. And then you become surly teenagers. And that's unfortunately the time that we try to teach you algebra. And they go, I'm a teenager now, I don't have to know this stuff. And then you become a 20-something, you're in college, you're struggling with your math class. I go, why didn't my algebra teacher teach me this stuff? And meanwhile, they're out there in the ether going, we did, motherfucker. You just don't remember it because you were a surly teenager. What I'm saying is that we have to move calculus all the way back to like elementary school when children might still trust us. And they're really good at just absorbing stuff. Get all the mechanics, all of it, back when they're kids. Don't try to explain derivatives and like tangents and stuff like that. Just have them do mechanics. They're really good at it. Anyway, maybe this is why I'm not allowed to teach in elementary schools. Now, Leach, you can't be teaching first graders calculus. Just watch me. Anyway, so we've already seen the del operator applying to a scalar function. When we apply del operator to a scalar function f, we get the gradient of f. That's the partial of f with respect to xi, the partial of f with respect to yj, and the partial of f with respect to zk. The del just gets written next to the f because f is a scalar function. So we're applying this operation to the scalar function f. Curl and divergence are both the del operator applied to a vector field. So if we take this del operator, let's write down our vector field. I'm going to say let's let f be a vector field, and it has three components: f1 I plus f2 j plus f3 k. So when f is a scalar function, we just apply the del operator to it. We end up with a vector, the gradient. Now, if we start with a vector field, there's two ways that we can find this del operator with our vector field: dot product and cross product. The del operator dot the vector field is going to be the divergence. The divergence is the scalar one. So that means we're just going to multiply, find the sum of the products of the corresponding components. In this case, the product is going to be the partial with respect to x applied to f1. Now remember, we're coming up with a scalar here. So we'll find the sum of the products, the partial with respect to x of f1. No vectors. Partial of f2 with respect to y, plus the partial of f3 with respect to z. Dot product is a scalar product. We ended up with a scalar. The del operator dot a vector field will be the divergence of the vector field. Now, this is a new thing that we haven't encountered before. When we applied del to the scalar function f, we know what the gradient is. We know what the gradient tells us about the function f. It's the direction of greatest increase in the value of the function. Steepest route up the hill. Perpendicular to the contours. But what does this divergence tell us about the vector field? Right now, we just know how to calculate it. We know it comes out as scalar. It's some number that tells us something about this vector field. And it's involved in this divergence theorem, which is a fundamental theorem of calculus. So this divergence is telling us something about how the vector field is changing, because that's what derivatives tell us. So this is what we need to think about. What does divergence tell us about a vector field? Why is this some kind of derivative of the vector field beyond the mechanics? The other way I can combine two vectors is a cross product. del cross F. This is going to result in what we call the curl of the vector field. And we know that the curl of the vector field is going to be a vector because it's the result of a cross product. To calculate the curl, we're just going to make a cross product. So del cross F and we can calculate our cross product in the usual way. Our first row is going to be I, J, and K. Our second row will be our first vector listed, which is just the del operator. In this case, I didn't really write this wide enough. I'll just have to go vertical on my del. Instead of multiplying, since these are operations, we're going to take partials with respect to the corresponding variables. And then on the third row, we'll put our vector field. Oops. The components of our vector field. We're going to calculate our cross products with cofactor expansion along the first row. So our I component, if I take out the I column and the IJK row, the partial of Fy, partial of F3 with respect to Y minus the partial F2 with respect to Z. So my I component will be the partial of F3 with respect to Y, that's this product, minus the partial of F2 with respect to Z. This is my I component. We're going to switch signs. We alternate signs when we're doing cofactor expansion. If I take out the row and column with J, I have the 2 by 2 partial of F3 with respect to X minus the partial of F1 with respect to Z for a J component. Switch signs again. Take out the K column and the K and the IJK row, and I'll have the partial at F2 with respect to X minus the partial of F1 with respect to Y. This is the vector curl of F. I find it easier to remember in this form, alternating I, J, and K. If we think about I as being related to F1 and the partial with respect to X, notice that the I component doesn't have any F1 and also doesn't have any partial with respect to X. Also, look at everything, if we think of F1, partial X, F2, Y, and F3 and Z as being if we remember that those are all in the same columns, notice that our partial derivatives never have a partial of F3 with respect to Z. Never a partial of F2 with respect to Y, never a partial of F1 with respect to X. It's always mixed. So there's no X, there's no F1. F3 with respect to Y, F2 with respect to Z. J is F2 and Y. Partial of F3 with respect to X, partial of F1 with respect to Z. K is F3 and Z. Partial of F2 with respect to X, doesn't match. Partial of F1 with respect to Y, doesn't match. The reason I'm pointing out these patterns is that you're not going to want to write this to remember the order of your factors and your terms. So look for the patterns of the things that are that match and don't match. And remember how we calculate with cofactor expansion. The I component is not going to have anything in the I column. So the I component has F2, F3, Y, and Z, and it's always mixed up. Partial of F3 with respect to Y, F2 with respect to Z. The reason that I like to keep the plus minus plus structure is that it goes 3, 2, 3, 1, 2, 1. It's always just that way you don't mix up the signs. How you will see this written out is that this negative will be multiplied into our coefficient of J and kind of mess up this whole pattern. This is 3, 2, 3, 1, 2, 1 with the plus minus plus. So to me, this means you have to remember more stuff. I think it's easier to remember the plus minus plus because you remember it comes from cofactor expansion because it alternates, you alternate signs. But sometimes you'll see this J component as the partial F1 with respect to Z minus the partial at F3 with respect to X. So it's like 3, 2, 1, 3, 2, 1. I hate that. I don't know why. But I think the primary reason that I hate that is so I can bring this up so we can sit there and look at this pattern more. Because y'all have spent more time looking at this pattern than just writing stuff down. You know what I mean? Also note that this vector curl is very similar to the scalar curl that we had before. The scalar curl was when we had a vector field of just in R2. So the partial F2 with respect to Y minus the partial F1 with respect. Partial F2 with respect to X minus partial F1 with respect to Y. The goal is less about writing this down, but we want to practice writing this down. We want to be able to remember our formulas for stuff. And that comes from remembering this part is stuff that should take place just in your mind. And you use this thought to write down your curl. This still raises a question, just like we had with divergence. What does the vector curl tell us about the vector field? We know what the gradient tells us about a scalar function. But what does divergence tell us about the vector field F? What does the curl tell us about the vector field F? It's these del operators in the fundamental theorem of calculus the curl and the divergence are some kind of derivative of this vector field. Derivative tells us how things are changing, but in what way does divergence and curl tell us how the vector field is changing? Any questions? So those are two outstanding questions that we have right now. Mechanically, we know how to calculate divergence and curl with this del operator. We know that they fit into some fundamental theorems of calculus, standing in as the derivative. But what do those two, what does del operator tell us about a vector field? Any questions? Comments? Deep thought? Difficult, just have more questions at the end than you did at the beginning. All right, that's going to do it for today. I will see you all on tomorrow. And we'll wonder, will tomorrow be the day that we find out what divergence and curl tells us? I mean, it's me, so probably not. That's it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.